Okay, I'll talk next. And it's interesting that I hear from everyone that we're trying to solve the problem of the equality of the slices of arrays, and we consider it as a very important problem because it's very painful and it's hard to people to debug it. And then we spent a few months to try to solve this problem and really solve it. And then after the release of Cloud 4, and we found it the model, the new frontier model can solve it automatically without any extra help. So then we start to come up with some ideas that whether we can create a benchmark that probably the dataset is not in the training dataset of the frontier model. So maybe it will beat the frontier models in some way. So I'm going to introduce our paper towards automated contamination-free Dafny benchmark generation. And this is a joint work with Mariano, Dejan, Marco from KTH. And as LLMs are increasingly used for code generation these days, but how to guarantee the correctness of the code is a major challenge. Formal verification is one of the strongest way to guarantee, especially for the code generated by LLM, because it can allow automatically feedback for LLM to refine the code is generated until it's reached a valid program. However, formal verification is always time-consuming and difficult, which limits its adoption in practice. So we also start to think that whether LLM can help verify the code, and we start with Dafny code verification. So now imagine that we have a Dafny program, which is method, func, and now the program want to verify it. So it needs to provide a set of contracts. Here we only use a post condition, so we define a func post and put it as a post condition in the method func to try to verify it. And the next step is, of course, try to write some annotations. And here we call it the auxiliary verification code to help the Dafny to reason about the program. This usually takes a lot of efforts by writing invariants, assertions, or even lemmas. So we especially focus on the generation of this auxiliary verification code. So the task becomes that given Dafny program and the Dafny contract, how can LLM generate this auxiliary verification code? So now we have a task. Then how to evaluate LLM the task? We need a benchmark. So, however, existing Dafny benchmark usually have several limitations. For example, this sometimes doesn't have a clear verification goal. Here we just need to generate the auxiliary verification code, but sometimes they also need to generate the specifications, a lot of code at the same time. And they don't have a defined structured difficulty level like easy, medium, or difficulty, and they are vulnerable to contamination because they always use the dataset publicly available, and most of them are manually corrected, so it's hard to scale. And in this work, we want to have a fully automated and contamination-free benchmark for evaluating how well LLM can verify Dafny code. So in this paper, we provide a fully automated benchmark generation pipeline for Dafny verification, also trying to converting some common programming language problem into Dafny verification task. We try to ensure the functional consistency between implementation and the contract by validated through some automatically generated test cases. We propose a contamination-free and a reproducible benchmark design to avoid data leakage. So now, the goal of our benchmarking is to create a set of tasks with, it's not working. Okay. With a set of, the set of tasks consists of a Dafny program and a Dafny contract to be verified. However, how can we get these tasks, and how can we also try to have a clear verification goal and structure the way of structure the definition of difficulty, and also probably can be potentially automated. That's why we also look into the same direction, try to generate this from some common programming context problem like the TACoDafny Marcus had mentioned before. So take this one as example from LeetCode. It's the first task in LeetCode. Given an array of indices, num and an integer target, return the indices of the two numbers such that they add up to target. So this is a very easy one, but we can see from the platform that they usually provide a solution already. This is usually in some mainstream language, for example, a Python implementation. So we already have a program, but we just need to convert it to Dafny. And it's also described in natural language about what the expected behavior of the program. For example, here, return the indices of two numbers such that they add up to target. So we already have a program and a contract, just in a different format. So the task of TACoDafny is try to converting them into a Dafny program and Dafny contract. So the first step of TACoDafny is take the task description to generate and prompt the LLM to generate a Dafny program called func without any syntax error, and so that we can try to run it. And in this step, we deliberately ask the LLM don't generate any verification code because we only focus on the program, the functional program. So to check this, we also ask another LLM to generate a set of test cases, including trying to cover all the edge cases and run it on top of Python implementation to get the output and makeup of our positive test cases pair with input and output so that we can test it on the Dafny code. We can run it. That's a kind of a good point of Dafny because we can run it. So if the output is the same, we can get a correct synthesized Dafny program, at least correct on the LM-generated test cases, and we try to uncover as most as possible. Otherwise, we provide a feedback to the LM to refine its code. Then, same for the generation of synthesize of Dafny contract. We extend the same way. We do the task description, ask LM to generate the syntax error-free Dafny contract func post I and O, and we can evaluate it. We can extend it from the last positive test cases generated in the last step, and we just want to make sure that the contract can evaluate to true on the positive test cases. But this is not enough most of the time, because we can actually define the func post in this way, say it's true, and it still can be evaluated to true on all the positive cases. So that's why we need some negative test cases. And to do so, we ask the LM to generate negative test cases pair with both input and output, and we validate it on the Python implementation as well. So Python actually is a ground truth for us. And we just need to make sure that the output of the Python is different from the output of the test cases, and so that we can get the negative test cases. Otherwise, we'll prompt the LM to generate another new negative test cases. So we have both positive and negative cases, so we can try to evaluate it. So as long as evaluate to true to the test cases positive, evaluate to false to the negative test cases, it's a correct synthesized Dafny contract, at least on the test cases. So we highly depend ourselves on the test cases. It's also our limitation, of course. And otherwise, we provide the feedback as usual. And we now have a contract that is consistent with both the positive cases and negative test cases. But this doesn't guarantee it's a strong contract. It's trying to capture all the specifications that we want, all the behaviors that we want. So there's a very preliminary solution here, is that we use model counting. So we ask LM to give us a finite search space definition called finite set, which take input of the input I. So we can count for each fixed input. We can count the output satisfying the contract using this, and we can output how many output that is satisfying this contract within this search space. And if there's exactly one valid output, the specification is extremely strong for us. But of course, this is, as I say, this is a preliminary solution. There's a lot of limitations, for example, because the search space is defined by OM. It could be too large or too small, resulting in timeout or zero solution. And it could be also some cases where model count is greater than 1, and it still have a very good contract. For example, in the two-sum example we mentioned before, if we have nums is sequence of 1 to 3, target is to 3, of course the solution is 1 and 2, because 1 plus 2 is 3. However, the text also saying that we can return the answer in any order, so solution could be both. Solution could be both 1 and 2 and 2 and 1. So model count is actually greater than 2, but we cannot say the formal contract that gives us this solution is bad. It's also strong. So how to give a smart threshold for this for the model counting, and how to give a smart definition of the search space remains the future work. And beyond specification strengths, we also care about the data contamination. And the key idea here is that TACoDafny is evaluation first, not dataset first. So instead of releasing the fixed benchmark instance, we aim at release only the generation script. So all the user can run the generation script and on all the programming tasks they want. And so instead of making all the dataset and example publicly available, so they can also try to choose some programming context problems after the post cutoff date of the model release. So in that case, the task cannot be in the training dataset of the LLM. So this helps us to try to remove the contamination and enable a fair and reproducible comparison. And as a preliminary experiment, we have our bench. We applied TACoDafny to the first 200 LeetCode problem. The reason why we didn't expand to a few thousand is that we are poor, kind of. Because we don't have $20,000 to spend to generate the benchmark. But yeah, so we after the execution, we used the Cloud4 Sonnet to generate the synthesized 76 executable Dafny program with contract to be verified, both of defining Dafny, and both has been validated by the generated test cases. And 51 of them has shown strong specification, which means the model counting is equals to 1. And the one that failing the validation usually means that usually ends up with a timeout because the search space was too long. It's too large. And for evaluation, the goal of a model is actually to generate the auxiliary verification code to help the code to be verified. And we use verified K as an evaluation matrix. K is the maximum amount of interactions with the LLM. And a task will be considered solved if the verification can succeed within K iteration rounds. And we set K to 20 in our experiments. We also evaluate our benchmark on several models, some proprietary models and open weight models. And here's the result. The x-axis here is the number of attempts. Y is the verified K. And we can see that Cloud4 Sonnet is the best one. There's a large gap between other models. And it can solve almost 40% of the tasks in our benchmark within 20 interaction rounds. But GPT-5, GPT-4, even they are also very big, very popular models. They perform much more. And not to mention small models like Llama 3.1, it cannot even solve one single task. And we checked the log of the small models, and we found that they're likely to take a lot of shortcuts by removing some verification tasks or adding a lot of assertions or cheating. And this shows that Dafny verification still remains challenging. And we can also witness that there's a performance improvement as the number of allowed interaction rounds increase. I also need to mention that by each interaction, we also provide the Dafny error message as a feedback. So that's why it's kind of helping the LLM to refine the verification code based on Dafny error messages. And it's actually helping it because we can see an incrementally increase of the performance. And the final takeaway is that the tasks that are easier to implement tend to be easier to verify as well. And the x-axis here is the difficulty level. And we can see when the difficulty level increases, the verification at 20 is also dropping dramatically. This is likely due to the complexity of the control flow. A deeper invariance needed, a deeper post condition to be much more complicated post condition to be verified. OK, to conclude. TACoDafny is a fully automated contamination-free benchmark for Dafny verification. And our results show that Dafny verification is still challenging, even for state-of-the-art LLMs. But our TACoDafny try to provide a fair and systematic evaluation. Beyond evaluation, actually, this one has already been explored because the previous speaker has already said that they use the dataset and the traces while synthesizing the code. They can use this dataset and traces to training a new model to make the model become smarter. And it's trying to help to bridge the gap between code generation and formal reasoning. And of course, there are a few open questions. For example, we heavily rely on the verifiability on the test cases generated by LLM. It can, at some cases, in the real software development process, there always exists some untested edge cases, and this can potentially make our implementation and the contract not verifiable. So we have some safeguard that because we manually check that most of the tasks are verifiable, and the model have a different performance difference. So this fulfills the goal of having a benchmark to enable a comparable evaluation. Another limitation is that TACoDafny now only support the generation of non-ghost specification because we need to execute the specification using the test cases. So how to support TACoDafny with non-ghost with a ghost-based specification is also a future problem. But thank you for your listening.
Do we have time for questions?
Very nice talk.
You mentioned 76 and 51 at the specification and then the model checking stage.
Yep.
What was the number at the implementation generation stage? So you have 76 programs with contracts. I'm just thinking about like the programs without contracts. Like, do you see?
We just we simply remove the one without contracts because like if there's a program without contract, like it doesn't make sense to keep them if there's nothing to be verified.
Right. But you take the Python and then you try to translate it into Dafny.
Yep.
Just wondering, like, how much do you end up losing at that stage of the pipeline already?
I think I didn't remember the number, but as I remember, the success rate from Python to Dafny is quite high. So like, I would say 150 out of 200, like this.
Thank you.
But the synthesis of the contract is much more difficult, and this is why it makes only 76 in the end.
Are the generated programs with the executable with contracts, are they actually available to read somewhere? Like, see what those generated programs are? Like,
you mean the readability?
Just the, you have generated some problems that are now verified, and are those problems like available online?
Like, we are not planning to release it because we don't want it to become a training dataset in the future model. But I mean, everyone can use a script. We will release a script, and everyone just run a script and training their generating the benchmark by themselves.
Which script? Because like part of this is like by LLM, so you provide like a library that will interact with the LLM. Like what is exactly your script doing?
It's a pipeline, the script of the pipeline generating.
The whole pipe.
Yes.
Plug. Okay.
Yep.
Any more questions?
Hi. Did you try evaluating after the model release cutoff date?
Sorry?
So, for example, a model was released at some point of time. Did you evaluate only on problems that were released after that cutoff date? And did you see any drop in performance of those models?
We did it, yes, actually. But the problem is that so the programming tasks after the cutting off date itself, the verification of it itself is not the same. The verification difficulty of itself is not the same as the one before the cutoff date. So it's like hard to compare because they are not doing the same verification task. But we can try to evaluate. We can try to keep the a potential direction that we can try to. Using different models that have different cutting off date and only evaluate on a bunch of fixed data set. But like, for example, a bunch of tasks, and we evaluate the model, there's a model created before this task and after this task, and we can compare the performance of different models. But this also depends on the different model, because models have different performance as well. We cannot make them exactly the same.
Okay, thank you.